Good afternoon, all. Thank you for joining our today's webinar on what is high-speed design. I'm Saira, working as Team Lead EDA here at the SAS Microsystems for All-Time Products. And today webinar is under recording. If anyone having any questions during the presentation or during the demonstration, please type your questions in the chat. We'll discuss at the end of the demo. Now, let us get started. Here we have the agenda for this today's presentation. First, we will discuss what is high-speed design in general. And secondly, we will discuss issues related to impedance. And the topic is reflections. We will look into that one also. Later, we have crosstalk. How will this impact our design? And we will present a demonstration showing you how Altium can help you in these matters. And we will see how to define a layer stackup and set up impedance profiles. Then we are going to use these settings to stimulate screen integrity and crosstalk. First, let us set a few things right. When we have a PCB track of a certain length, that length is also a delay in time or a flight time. And one good length to remember is 150 mm. This is approximately 1 nanosecond. That means if you have a signal length of 150 mm, that means approximately it is 1 nanosecond. And also we need to understand we are using a transmit signal with especially the rise and fall time are important. You can see nowadays rising device rise time and fall time means switching time. Nowadays, many modern devices has rising and falling at just 100 picoseconds or less, which is equal to 15 mm fraction. This time is for 10% to 90% of the signal level, or in other words, the time it takes from logic 0 to 1 or 1 to 0. And the second picture with this is showing the crosstalk, whereas which we will go to address later. And if you look at here, a test from Lee Ritchie, which is a speeding edge consultants, shows that problem reflections starts when the track, when the length of a track is of the switching time. So basically, we see issues already at 7.5 mm tracks when switching time is 100 picoseconds, and the crosstalk issues at 1 by 4 of that, so 3.5 mm of track length. This is how the reflections issues will happen, causing overshoot and crosstalk issues like this. And if you take a look at the impedance, here we have the layer stack of our printed circuit boards. Like this PCB, we see that the layers are stacked upon each other. First, we have some overlay to protect the outer copper from corrosion, and perhaps also a overlay or fill screen with the components designators. Then we have the copper layers, and those are separated by some dielectric. This dielectric can then be of various thickness, basically making sure the copper does not make shortcuts from layer to layer. This is how the stack up will be built, and this also matters when you are calculating the impedance. Some incidence considerations: when we have a stack up, we have two planes or tracks of copper, and in between them we have some dielectric. This is basically how to build a capacitor. The capacitor size is determined upon area of where the planes or tracks overlap. The distance between the planes and the type of dielectric. This capacitor will of course have a great influence on the impedance. Basic, we don't want the cap, but we can't avoid it due to the fishing. We can, however, minimize it with carefully planning the stack up and routing width. That means impedance can be controlled by controlling the track width. And here, if you look at the other aspect is transmission line. We need to consider when making a connection between two components. Here we have see a simplified model of transmission line or a track. And notice that the energy not only runs from source to receiver, but also have to combine in a closed loop. Okay, this is how a transmission line looks. Is after source destination, and he has to come back to the source. It's called a closed loop. That's how signal will get transmitted. One of the way we can adjust the impedance is width of the track, as I told earlier. There are others, but the width is one with most influence on the impedance. When you have the impedance calculator, you will be, in RTM, you will be entering the proper stack up and you will be taking our impedance certain path in the impedance calculator. Later, based on the impedance value, what we require, when you click enter the value of impedance tolerance, the tool will automatically give the track. That's what width is being plays a key role in controlling the impedance. And we want to achieve impedance match so that we get a well-defined signal without overshoot or undershoot. Left picture, we see a signal with perfect impedance match. Right, we see some overshoot on the rising edge and also some undershoot on the falling edge caused by mismatch impedance. You can see here, this here, there is no overshoot and undershoot happening, but here in the right side of the image, there are rising edge, undershoot, rising edge, undershoots, overshoot, undershoots, and falling edge, undershoots and overshoots happen because of the mismatch impedance in the signal. I mean, in the transmission line. Now let us see about the reflections. We start to see with reflections when the tracks are of the length of the rise time, which will be defined by Rigi from a company called Speed Edge. So if the rising edge is 100 picoseconds like many modern ICs, track longer than 7.5 mm should be considered as high speed. What are the causes of reflections? One is poor impedance mismatch, and other one is steps on the PCB track and bias steps. They are the main causes for the reflections on the track. Okay, unused tracks, just like this, and steps on the PCB and bias steps. Bias step means unused BR. This is called the bias step, which will be causing main cause for the reflections. And crosstalk. We start to see issues with crosstalk when the tracks are 1/4 the length of the rise time. So if the rise edge is 100 picoseconds like many modern ICs, the tracks longer than 3.75 mm should be considered as a high speed. What is crosstalk? When we talk about the crosstalk, we use the term aggressor for the track that being driven and victim for the track that runs along the aggressor. See, this is the transmission line. This is a driven line called a aggressor, and this is called as a victim line. See, driven line here is having some data is been getting transferred, and this victim line, which is very close to the, which is very close coupled to the driven line. Notice what happened. There is some crosstalk happening. See here, we have got the rising edge crosstalk and falling edge crosstalk. This is how you can able to get the crosstalk when you have the two signals close by, when the other signal will get fed the same data. To avoid this, we need to maintain a sufficient gap between your high and low frequency signals to avoid the crosstalks in the design. Now let us see with a quick demo how we can able to perform this reflections and crosstalk analysis inside the RDM designer. We just have a look with a demo. Yes. Now I'm in RDM designer. I have opened a small example here to demonstrate the capabilities of signal analysis inside the RDM designer. And before we run the signal integrity analysis inside the RTM designer, first we need to make sure that particular extension get installed or not. To do so, go to here, extension updates, and then purchased. You see, make sure that signal integrity is being installed, which will demonstrate with a tick mark. If you don't have, it will be showing as a download symbol. Then click on that and restart the alternate designer, and you'll be able to see under install signal analysis. Okay, this is a very important thing everyone should follow. Once this is getting installed, we are good to perform the signal integrity analysis. For performing the signal integrity analysis, you need to have the model files to be added to your components. I mean, IPS files need to be added to your component. Now, let us see whether we have added the IPS file or not. If you double click the component, you can able to see the IPS file. This is the one we have. We have the IPS file as in this path, and we have got the pin models. These pin models show the what is the state of the this one, and we have taken the typical case. Why we need the IPS file means IPS file will have the information about the how the pins reacting with different with various voltages. Okay, that information will be there in the IPS file. And if you take a look at here, we have got this some model type. We have got some four cases. We have got strong case, typical case, and weak case, which I'm going to take now strong typical case. Typical case means the data will be obtained for nominal supply voltage, nominal temperature, nominal parameter process. If you select a weak model, the data will be applied with low supply voltage, high temperature, and weak process parameters. And if you take a strong case, the conditions will be higher supply, low temperature, and strong process. This is the way you have to solve the types. But here I'm going to use the triple case, and I got the motorcycles, which I got the voltage selection. We have selected the 3.3 volts as a voltage selection for this. Okay. And in RTM for signal analysis, we can do pre-layout and post-layout, and crosstalk simulation can be performed. Pre-layout means without having PCB, you can perform the signal integrity analysis. Okay, and at the PCB side also, you can perform the signal integrity analysis like we have impedance, and crosstalk analysis can be performed on the PCB only. We can't perform it on the schematics. Okay, now let us run the analysis, and before that, we have set some design rule for the supply net. How I set is we have placed some directives, and double click to open the properties, and we can just click on add a rule, and we can go here signal integrity, and we can able to select the supply nets, and you can have to specify what is the voltage you want. Voltage for ground and VCC, you can perform the voltage and click OK. Automatically the voltage will be shown on the net. Okay, this is very important. We have to set the supply voltages for the nets. Okay, once the supply voltage has been set, now we are good to run the S analysis on this particular sheet. To do so, go to tools and say signal integrity. When you perform signal integrity, the tool is going to run the analysis, and it has showed a few nets pass and few nets failed. It's showing D5 to D5, D4, D6 net got failed. That means D5 to D6, D7 nets got failed. Why? Because they don't have any kind of terminations inside the nets. That's the reason the signals got failed. Okay. Now, how we can run the analysis for this one? Just click on this net. Self-tested want to see the what is the issue with this particular net. We have to check what is happening inside the net, or where that has been lost. We can able to see the things. Okay. Now I have chosen this one net which was failed. I want to see why it got failed. I want to see the analysis. Just select this net. Just click on this arrow to have the net to be analyzed, and we have to run the analysis without terminations. And then just click on reflection waveforms. I click on reflection waveform. See here, we have got the D4 net. There is some rising edge overshoot and undershoot happening, and falling edge undershoot overshoot happening. And when you see at the this is transmitter, this is transmitter, this is the receiver. At the receiver side, you are having more kind of rising edge overshoot and undershoot happening, and also falling edge undershoot and overshoot happening. That's the reason this set has been failed. If you add termination in between this line, you may overcome the challenge. Now let us enable the termination, and let us choose a value of 39 ohms. Let me choose a value of 39 ohms, and I'll just click on reflection waveforms. Yes, now see here, without well, let's put this one down. Without the any kind of termination, you can see there is no problem here. There is a problem. Yes, there is a problem like we were. Now with termination of resistance 39 ohms, sorry, 39 ohms, you can see there is a steep curve, rising edge and falling edge as a steep curve. There is no kind of issues in the signal. That means we need to add this 39 ohms resistors inside the our schematic sheet, and if you can perform analysis, you will get the proper output. Okay, like you can able to have that, and also we can have the sweeps also can be performed. We can able to enable perform sweeps, and we can able to perform the sweeps for number 5, and you can also control this one starting from 10 to 40 ohms. Okay, let's say 10 to 50. Okay, not 40, 50. Let us 50 ohms will take, and for 5 reflection waveforms. This is for termination. This is with 10, 20. Now let me close it and again read and so that we'll get a one single window. It will be good compared to that. Yes, this is what I require. Yes. See with the no termination, with a value of 20 ohms, okay, 30 ohms, 40 ohms, and 50 ohms. This is how we're going to easily perform the sweeps inside the schematic. And also we have an option to set this some options. If you go to the menu, you can able to set up options. If you go, you can able to set the what is the track impedance is allowed, and what is the average track length, and what are supply next, because we are told to pick the supply not from the rule. That's why this bit option is enabled. If you don't have, you can able to pick supplies from here. If you want to feed any similar signal to any pin, you can able to feed from here. Okay, and also you can able to set the tolerance. See here we have set the tolerance for the top value 110 as a percentage attribute for the falling and rising edge to pass or fail the signal. Okay, this is how you have to basically do the signal analysis inside the biologic schematics. Now let us push this design to the PCB, and let us see how we can perform the signal analysis at the PCB side. I have the PCB being created by me already. I'm going to add this to the project to perform the SI analysis. Now this is the PCB where I have the two ICs has been placed, the tracks on the both the layers, top layer and the bottom layer. Now I want to perform the signal analysis by this PCB. For before that, we need to import the changes from the project. For that, go to design, import changes from project. Yes, to synchronize the schematic and the PCB. Yes, validate use changes. Now we need to set this stack up. And this, go to design, layer stack manager. Now I think you can know this is the layer stack manager. We have got the 4 layer, and we have top layer 1, and we have 2 dielectric materials, and I have dedicated plane layer for the ground and VCC, and the bottom layer. And I got the impedance profile, which we got some messages out of date. That is updated. This properties. This is the 50 ohms impedance based on the stack up by using the proper thickness. If you see, it is recommending 0.469 is a track width to achieve the 50 ohms impedance. And for this also, if you want a 50 ohms impedance to tolerance to 10%, this is a track width it's been recommended. This one you can able to apply single click in the design rules. It is save the stack up and go to PCB. Now we need to see our design rules. Just go to design rules. Let me re-update so that the tool will have don't have any issue. This is the way the design rule has been easily updated from the layer stack manager without updating manually. 0.447 is the bit which is being taken for 50 ohms. This is how you can simply get the rule values updated for this one. And we have the other rules here for the rising edge and falling edge. Okay. Apply and okay. Now on the signal analysis, so I'll just go to tools and say signal analysis. Now here we can see that it's been passed, but you can see we have got the massive overshoots happening here. You can see here massive overshoots happening, undershoots and massive overshoots happening in these two kind of nets. You can see here very less here. Why? Because let us see, it's been set as a 300 volts. Now it is changes to 0.3 to get the this 0.3 volts, 40 millivolts. You want to allow only 30 millivolts only wash undershoots happens. Let us see this one is 30, 30, 30, 100 millivolts. Okay, and again see when I set this value to 300 millivolts, again this is 4 nets got failed. I mean D4 to D7 where behind the schematic you see, those nets got failed. Okay, even if I change the impedance, let us see, we will change the impedance. Okay, now go to design layer stack manager. Now let me change this impedance to 75. Let me close this 75. Let us see, this is the track width. Go to PCB, save this, go to PCB, design rules, and width rule. Yes, update to this one and update the track width here because track width got changed, right? We have to update track width, root, it is selected, and shift S to back, and again run the signal analysis to see the same place got paused. That means there is no change at all. If you even change the impedance, these are all are within the stipulated time. Now This how you can able to play with the different impedance values, and you can able to play the different values of understood and rising edge values inside the ultimate. Now let us take a look at the cross-talk analysis inside the LTM. If you look at these bottom layer signals for D4 to D7, they are close by a coupled. We want to see are there kind of reflections happening, sorry, crosstalk happening between these signals with reference to D4. Now let us add these signals for the analysis purpose. Let us take this as a you can see cross probe, and you click on the signal, you can have to cross probe between the schematic. Let us make it as a aggressor, and let us make it as a all as a victim. And I don't want any kind of terminations. I want to see with respect to this signal what the crosstalk happening with the other signal you want to see. Just click on crosstalk waveforms. When I click on crosstalk waveforms, this is the D4 signal which has been failed because of the more understood and overstood values that we already know. Okay, and if you look at this one, D5, which is having a noise with respect to this particular signal of 750 millivolts, which is more considerably, which is not acceptable. And if you look at this one, other signal D5, there is much less than this one, which is nearly 150 millivolts. And this one also is same 150. This is also having a higher value only. Okay, just having higher value only. Okay, this is having lesser 50 millivolts. This is having almost 300 millivolts of crosstalk happening. Then also having 50 millivolts. That means these signals having uh, more of see this are having more than 400. This is having more than 400. This is also more than 400. Okay, means as a rule that the crosstalk should not exceed 300 millivolts in the signal. If it is exceeding more than this value, you should consider giving more space between the signals tracks were routed in the design. This is all about the today's topic. What is XP design and how we can able to do this analysis inside the RTM, like impedance, reflection, crosstalk analysis inside the RTM. Now we are open for the questions.